So my name's Trip Humphries. Just another quick slide on what's going on at the lab. But again, it just kind of reiterates we kind of cover everything in various forums across the lab. Our group in particular, like we're full life cycle, so we have folks all the way down at board level, designing custom boards, microwave, digital boards, up through firmware, embedded software, and then we actually build these systems and then field them. So we're touching every little piece of this, and it's it's really cool to see all that. So like I said earlier, we're kind of in this realm of like rapid growth. I think this last year, and James, correct me if I'm wrong, I think we just cracked $1 billion in sponsored research, and it's continuing to grow. I think our lab leadership, whether it's realistic or not, don't quote me there, they're wanting to get to kind of push to the 2 billion mark, which is great, but we don't have enough people to do all that work. So if you are interested in coming down to Atlanta and want to do weird stuff with SDR, let me know. I would be happy to talk to you about that. Our presence is all over the United States. Of course, our main labs are in Atlanta and Smyrna, but we kind of cover California, Northeast. Somebody is at our field offices in Germany. I didn't know we had field offices in Germany. I'm super jealous, so I think it's time we made a move there. So I'll kind of get into the meat of this out-of-tree module. So pulse descriptor words, that's exactly like what the name implies. It's a measurement that describes a pulse. So we do some sort of pulse detection, and then we take the the IQ data that's in there, we do characterization. So pulse width, pulse power, pulse frequency, what kind of modulation is on the pulse, what polarization do we detect, time of arrival. There's really no limit. If there's another measurement you want, you can add that to it. And so kind of the advantage is that we can kind of par down this IQ data into pulse descriptor words. And kind of an example here on the right is 2 files that I recorded recently. So 1 megahertz sample rate, 30 seconds of data is 240 megabytes stored on my drive. I run that same data through gr-pdw, and just describing the pulse, we have 1 megabyte of data. And this is like a 1 kilohertz signal, 5 microsecond pulses. So that's really what we're looking at. Now this is kind of a trivial example. Our kind of top of the line systems are 1 gigahertz sample rate. So as you can imagine, this scales horribly for storing IQ data. And what we're trying to do here is kind of bring these tools into the software radio realm so that we can use them basically anywhere. And so kind of the motivation behind this work is we have tools in the lab that are your standard Keysight or Tektronix test equipment. And they can measure, they can do this. You can input a pulsed waveform. It will spit out a table of pulse descriptor words. You can save that and you can do that. The one that I got to play with at our lab, I think cost $250,000, so it's not fun to begin with. And then they also want to charge you for the software to do that. So you buy the hardware, then you got to buy the license, and then you got to figure out how to use it. And which is great. I'm not trying to say that their hardware is bad or their software is bad. It's really amazing. But it's very cost prohibitive. Nobody likes it when I take these out into the field because they want it in the lab. I like kind of portable things. We're in the field a lot. I don't want to drag this stuff into the mud and dust and whatnot. So we're kind of sitting there and it's like, oh, well, we have 1 million SDRs laying around. Why can't we just use GNU Radio to kind of start building the tools to do this and make it open source so hopefully you guys don't have to buy this stuff. And one of the questions I get is like, well, you're a lab. What do you mean rugged environments? So like I said, we're full life cycle. So we're building, testing, and then taking these things into the field and running them against like, US radar assets, things like that. So on the top left up there, our rugged environments sometimes exist of like all of us crammed into a hotel room, frantically fixing bugs in between missions. The top Middle is like, we'll have our pods on aircraft that we fly out of Cartersville. And this is rugged because I'm trying not to throw up in the middle of that plane that picture was taken. You have me on the right, like in a mud pit. Just someone gave me a stick and was like, "Can you please get the mud out of here?" So, and then weird, creepy stuff like we walked into a building and there's just like "Fear Me" and all these nasty things written on the wall. Some of our folks, that helicopter is on the ground because engine warning light came on and they had to land the helicopter, but we had our folks in that helicopter. Luckily I wasn't in there, which was good. And then we do like nighttime ops. So kind of just going back to that point of like, we have all these crazy environments that we're working in. I have all these SDRs that I can work with. They're way cheaper than most of these other systems I can buy. Just pull them out of your pocket, start taking measurements. I want to walk around with it, generate this characterization data, take it back to my computer and kind of analyze it and see what's going on there. So gr-pdw, like I said, it's an out-of-tree module, so, and it's just there to do pulse descriptor word measurements. The goal is that it's kind of agnostic to the SDR platform. Some things that are specialized in there right now are the power calibration tables. You don't need to use those, and you could provide your own as well. So there's 4 or 5 kind of main blocks that are included with gr-pdw. So pulse detector block is trying to emulate kind of roughly what our firmware would do in the FPGA. So it finds the start of the pulse and the end of the pulse, puts a tag on those and sends them downstream. There's a pulse measurement block, so that one extracts the IQ in between those tags and does all this pulse descriptor word measurements. So pulse width, pulse frequency, pulse power, time of arrival, I think are the ones in there. It's super easy to add more if you wanted those. Some other utility things, so PDW to file will write those PDWs to a binary file. For offline analysis, you just want to log data. I will include a Python script that can open and read that file, so it'll pull it in as a pandas data frame, or you want to output a CSV or whatever. That's there. Calibration table, so user selects a reference value, a reference level. That will automatically select the gain, and so you can have calibrated power measurements for your pulse. And then a plotting function, so if you just want to play your flow graph, it will plot the PDWs as they stream in from your SDR. So this is kind of your typical flow graph. On the left there, this is kind of a simulated flow graph, pulse generator with a signal source to kind of provide some frequency input there. But kind of in the middle right, there's the pulse detector block. So that just adds those tags to the stream. Goes down to the pulse extraction block where it's doing all the PDW measurements. That spits out PDW messages. So that can go PDW to file, write all those out to a log file. That can go to the PDW plot. Or you can even put that into like a ZMQ sync and send them out over a network. We've done some testing with that. And so this one is just kind of a virtual example to play with. I include that in the module, and then there's a USRP-based flow graph as well. Pulse detection block, so like I said, all it does is assume some threshold value, which you set. You can update that as you go in real time, and then adds these tags to the pulse stream. And that's all it really does. So the output, you'll see these tagged pulses. And there's also a kind of debug signal, which is just the derivative of the input stream, and you can kind of get an idea of where the start and the stop of the pulse should be. The pulse extraction block, so it's looking for those tags in the stream, extracts the IQ in between those tags, and then does the measurements on those. So like I said, a PDW, one pulse descriptor word can have multiple measurements in it, so pulse width, again, pulse power, pulse frequency, time of arrival, and whatnot. PDW to file, so like I said, it takes this input stream of messages, dumps them into a binary file for later analysis. I do provide a tool in gr-pdw called pdw.py. So you just point that to your binary file, it will load it in, and you can use it as a pandas data frame, do some stats on it, dump it to a CSV file. You can load it in, manipulate the PDW measurements, and write them out to another file if you wanted to. So it's just a general tool for that. PDW plot. So it allows you to select one of 3 measurements, so you can plot pulse power, pulse frequency, and pulse width. And then those just drop into your flow graph, so you can see in real time like what's coming out. So no external tools required. You just plug your messages into this. It will plot those, and you can see it happening in real time, like pulse width changes, frequency changes, power changes, all kind of part of this package. And then calibration tables. So the nice thing about UHD is it comes with that kind of power calibration utility. So we wrote some code to automate that process with just an off-the-shelf signal generator, so that calibration process runs. You can save that table as a pickle file. This loads that table in and then sets those gain measurements based on a reference value. So on the right there is just some measurements across frequency. So you can see we're maybe 1 dB off all the way through 6 gigahertz for pulse power measurements. And on the bottom right is, we're with a reference value of minus 20 dBm, we can see pulses all the way down to minus 70 dBm. So you can kind of cover a pretty wide range of values. As you can imagine, in the lab it's fine, but when you're looking at a real radar, these signal levels can vary a lot depending on where you are. Also include a pulses.grc file, so it's just a hierarchical block that lets you define, amplitude, pulse width, and PRI, and then it will just spit out rectangular pulses. I use it all the time for a lot of things, so that's included in there. You just run it and put those values, and away you go. Showed this already, but this is virtual mode, so that flow graph is in there if you want to start playing with stuff. Just generates pulses, add some frequency content, some noise, and then you can see your PDW streaming out. And then USRP flow graph mode, so just a USRP source, passes it through the same exact blocks, extracts pulse measurements, writes them to a file. And you can see the calibration table on the bottom left there. I don't know, do we have the PDF slides or the PowerPoint slides up to the folks in the back? Well, there we go, nice. So this is what it would look like, and again, like you can place these plots and stuff wherever you want. Each one of the PDW plots is independent, so you can play with those as you want. So this is virtual mode, and you can kind of see the top 3 plots up there kind of changing as you play with PRI and pulse width and pulse power. So that's available right out of the box. You can start playing with that kind of thing. And let's see. And so we were just playing around in the hotel last night doing some wireless measurements. So James set up a little surrogate radar on the right there. And then I set up another SDR with gr-pdw running. And I think this is a video as well. Okay. So it's just a quick demo. So kind of James is over there like changing things without my knowledge, and we're accurately measuring the pulses that are coming through, which was kind of fun. And so we have done some quick measurements. We have an air surveillance radar right up against GTRI at Dobbins Air Base. So we do take students out to do fun stuff like that. But that's kind of like where we want to go with this, is being able to go out and do signal intelligence, open source, low-cost tools. Okay. So it will be available on GitHub, soon, trademark. Just cleaning up stuff right now. We have full permission to release open source code. It will be at that URL right there. That QR code points to that URL, so there's nothing nefarious behind that QR code. Probably next day or two, I'm just cleaning up some stuff right now, making sure there's not any glaring issues. That being said, I am happy to take pull requests. So I don't know what I have to say to get the internet all riled up and making people fix things because they think it's bad, but that's what I want to say. So you see things you want to add, fix, change, modify, please submit a pull request. I'm happy to pull that stuff in. And some future plans. So these are things that we're actively going to do soon. Right now, all the blocks are in Python. It runs relatively well. The low-hanging fruit is porting all that to C++. Improved plotting and visualization, so there are some hiccups there. Modulation detection is an important one. Exporting IQ, replaying PDW files through gr-pdw. And then on the right is kind of like an example of like using custom GUI. So this one actually listens for a stream of PDWs from the flow graph over a network and plots them in real time. So you can adjust threshold values, frequency, all that remotely. And one that I'm particularly interested in, and we talked with MathWorks about doing a demo of targeting an RF knock kind of workflow to do all this in FPGA land, which would open up a lot more application space for us. And that's it. So I'm happy to take any questions. If you want to come play with stuff, I'm hiding over here on the side. But yeah.
The energy detector piece seems like it's kind of doing a lot of work. Like if that piece doesn't, the detector block that you put up front.
Yep.
And there's a threshold to tune. So in like the practical example you showed us when you had a horn as a surrogate radar, if I move things twice as far, you have to go dial in that threshold again, right?
Yep. So yeah, you can change that threshold as things change.
And how do you, let's say on the fly, you're out in the field and you're testing this and you're not getting any detections, what's the process for figuring out feedback for how you need to tune that threshold?
So yeah, that kind of varies, environment to environment. So sometimes we combine this with like a field fox, like a portable kind of spectrum analyzer. I'll also kind of just run like a simple flow graph just to kind of dial in like, okay, what's the signal look in the time domain, so I can see that. There also is a plot when you run it, like in the example flow graph, showing you in time what those signals are looking like, so you can.
Got it. And then one follow-on too about that detector. So is it a pure time domain energy threshold?
Yep.
So in the case where you have like multiple radars at different frequencies, your detector would just declare the whole frequency band as having a signal in it, right? So have you thought about different architectures to have some frequency separation as well?
So yeah, that's something that we plan to work on. Right now, yeah, it's just kind of emulating what we do in firmware land. But the idea is that there will be different detection threshold techniques that you can apply depending on what you want to try to do.
And then finally, have you tried to use any of this, like just looking at commercial, bands? You've got usurps, have you tuned it to 750 megahertz and just see what comes out? You've got 3 LTE carriers there, how does your system perform under a real comms background? Because it's not designed for it, right?
So I haven't actually tried it against comms, but I have tried it against, just your standard air surveillance radar that would be sitting in an airfield. And I think that's 2.6 gigahertz. So yeah, it works well for that kind of thing. But
Yeah.
like I said, it's going to be available, so please let me know how it works for that stuff.
Yeah, and I'll just say real quick from the side over here that most of the radars are not going to operate within like 30-ish megahertz, so you can really kind of move around in there. They cause too much interference with each other to do that. They're putting out too much power, basically, most of the time. Another thing, when we're like looking for radars with this, it's pretty easy to take kind of just a wide band kind of spectrum analysis, right, and see where kind of everything is falling and then tune into those. But the SNR and power-wise, they're putting out so much, kilowatts of power usually that you're going to have to desensitize most of the time rather than increase your sensitivity based on distance. So, 10 kilometers, 20 kilometers from a really high-power air surveillance radar is like pretty easy with this kind of stuff. Yeah, and then they all have to operate on different frequencies just to be able to do air surveillance in the same localized area. So if you went to your random airport near yourself, you'd be able to see that you might have several different radars and they're all going to operate 30 to 100 megahertz away from each other.